In a previous video, I discussed how in predicate logic, the order of quantifiers does matter. And in this video, we're going to take a more mathematical approach, so to speak, in the sense that we're going to deal with propositions with functions in them. And this is something you will study if you're taking a discrete math course or a math course on proofs. For example, if you have a proposition such as for all x, there exists a y such that f of xy, that proposition has a function in it. But it wouldn't be equivalent to this proposition. There exists a y such that for all x, f of xy. The order of quantifiers matters. But here's one way to look at this. We can see they're not equivalent by thinking in terms of what makes a given proposition true or false. For instance, take this left-hand side. For all x, there exists a y such that f of xy. When is that proposition true? For every x, there exists a y, some y value, such that the function holds, such that it is true. And so, we can say for all values of x, there is a y value that makes f of xy true. So for all values of x, we have a y value that makes f of xy true. On the other hand, we can consider this proposition, which again, as I said, is not equivalent to the last proposition. There exists a y such that for all x, f of xy. We'll ask the question, when is that proposition true? So there exists a y such that for all x, f of xy. In other words, there is a single y value that makes the function true for all values of x. There is a single y value that makes the function f of xy true for all values of x. So there's a single y value for all values of x. Or in other words, we might think of y as being a constant. It's a single value. So we can say that y is a constant single value. Whereas for all x, there exists a y such that f of xy, we might say that y can depend on x. So it's variable. How about two examples of this? And in this case, I'm going to take these examples from a very popular book called How to Prove It. A lot of math courses assign this textbook for math majors. So let's say we have the following examples. We have for all x, there exists a y such that x is less than y. The domain is just all real numbers. And we just want to know, is this true or is this false as a proposition? And we want to compare that with there exists a y such that for all x, x is less than y. Again, the domain is just all real numbers. And we want to know, is this true or is this false? So the first example, for all x, there exists a y such that x is less than y. In other words, for every value of x, there is some y value out there such that x is less than y. Well, clearly, if you think about it, that has to be true, because you can always find a y value that's greater than any x value, right? So for example, let's say x is equal to 100. Well, then we'll just say that y is equal to 105/10. For every x value, you can find some y value that's greater, where both x and y are real numbers. On the other hand, what about this proposition? There exists a y such that for all x, x is less than y. In other words, there is some single y value that's going to be greater than any x value you pick, where both x and y are real numbers. Well, that's clearly false. Why? Because there is no single y value that's greater than any x value. So let's say that we say y is equal to 100. That's some specific value. Is that going to be greater than any x value we pick? Well, obviously no, because x might be 101. So there is no single y value that would make that hold. So let's get back to thinking about different types of propositions. So, for example, I already said we can have something like, for all x, there exists a y such that f of x, y. That's one possibility. It's a good proposition. We can have something like, there exists an x such that for all y, f of x, y. That's another possibility. We might have, for all x, for all y, f of x, y. Alternatively, maybe something like for all y, for all x, f of x, y. We might have there exists an x such that there exists a y, f of x, y, or there exists a y such that there exists an x, f of x, y. What would make those statements true? What would make them false? So when is this true? When is this false? So it's true, as we said, when for all values of x, there is a y value such that the function holds. But when would it be false? Which is also a very good question to ask. It would just be the contradictory of them. And so we would have, when there is ax such that f of x, y doesn't hold for every y value. And notice that it really is the exact opposite of being true. So instead of saying for all x values, we're just talking about for just a single x value. Instead of talking about just a y value, we're talking about every y values. And what about this? There exists an x such that for all y, f of x, y. So when is this true? And when is this false? It would be true when there is a x value such that the function is true for every y value. But when would it be false? Just be the contradictory of that. It would be false when for every x value there is a y value such that the function is false. Again, notice it's a direct contradictory statement. So here we have when there is a x value, but here every x value. Here we have for every y value, but here we just have a y value. Likewise, let's ask the question for this. For all x, for all y, f of x, y. For all y, for all x, f of x, y. when would these propositions be true? And when would they be false? So it would be true when the function is true for all pairs of x, y. When would it be false? When there is a pair x, y such to make the function false. So it's true when every pair makes the function true. It's false when you just have at least one pair that makes it false. And finally, there exists an x, there exists a y, f of x, y. There exists a y, there exists an x, f of x, y. We can ask the same question. When is it true? And when is it false? So it would be true when there is a pair x, y such that the function is true. That just means it exists some pair. And so if it's false, what would that mean? It would be the function is false for every pair x, y. So any pair you put in there, you always get a false statement. And that indeed is exactly contradictory to what makes it true. Let's think of a few more examples. So let's say we have something like there exists an x such that there exists a y, x squared plus y squared is equal to 5. But this time the domain is restricted to the integers. So the question is this true as a proposition or is it false as a proposition? So there exists an x, there exists a y such that x squared plus y squared is equal to 5. We just need to find a pair, x, y, where that statement is true to say it is true. So you just have to play around with some numbers and we'll find that this is true. For example, we can say that x is equal to 2 and y is equal to 1. Both are integers. We then have 2 squared plus 1 squared. That's 4 plus 1, and that's 5. And so we have an example where we have a pair, x, y, that makes this statement true, so it's a true statement. How about this? For all x, for all y, for all z, we have z is equal to x plus y over 2, and the domain again is restricted to the integers. So we want to know, is this true or is this false as a proposition? Is consider different numbers. And pretty soon you have to notice it's false, right? Because for example, let's say that x is equal to 3 and y is equal to 2. 3 and 2 are integers, but z wouldn't be, right? Because we would have 3 plus 2 over 2, which is 5 over 2, but that is not a member of the integers. So it's not the case that for every x, for every y, for every z, that proposition holds, that function holds, so to speak. On the other hand, notice that if the domain was changed to the reals, then it would be a true statement. Because 5 over 2, for example, is a real number. Okay, you can always get an average out of real numbers to get another real number. Or how about this? For all x, there exists a y such that 4x minus 2y is equal to 0. The domain refers to the real numbers. Again, is this true or is this false? And then we'll consider there exists a y such that for all x, 4x minus 2y is equal to 0, where the domain is just the real numbers, and we want to know, is the proposition true or false? So here we have, for all x, there's some y where that statement is true. And that has to be true, right? Because consider, let's say, the function there. 4x minus 2y is equal to 0. And we can just solve for x, for example. So 4x is equal to 2y. So x is equal to 1/2 y. But for any value of x, there is a value of y that makes our function true. So you always will find some y value to make that true. Or maybe I should have solved for y in that case, but at any rate, it doesn't really matter. But on the other hand, there exists a y such that for all x, 4x minus 2y equals 0. Is that true or false? So there is a single y value that makes that true for any x value? Well, that can't be. Right? So for example, if x is equal to 2, then what would y be? Well, y would be 4. But if x is equal to 4, then y would be 8. And clearly 4 does not equal 8. So there is no single y value for any x value that makes the function true. That's why it's false. Anyhow, I hope this video has been helpful. Thinking about what makes any given proposition true or false is a powerful way to consider the differences between propositions. The order of quantifiers makes a difference. And I do think mathematical propositions especially illuminate this. They also force us to consider contradictory relations by thinking about what would make any given proposition false. Thank you for watching, and good luck to you.